What does it mean to have a Bitcoin? Many people have heard of Bitcoin, that it's a fully digital currency with no government to issue it, and that no banks need to manage accounts and verify transactions. And also that no one really knows who invented it. And yet, many people don't know the answer to this question, at least not in full. To get there, and to make sure that the technical details underlying the answer actually feel motivated, what we're going to do is walk through, step by step, how you might have invented your own version of Bitcoin. We'll start with you keeping track of payments with your friends using a communal ledger, and then as you start to trust your friends and the world around you less and less, and if you're clever enough to bring in a few ideas from cryptography to help circumvent the need for trust, what you end up with is what's called a cryptocurrency. You see, Bitcoin is just the first implemented example of a cryptocurrency, and now there are thousands more on exchanges with traditional currencies. Walking the path of inventing your own can help to set the foundations for understanding some of the more recent players in the game, and recognizing when and why there's room for different design choices. In fact, one of the reasons I chose this topic is that in the last year, there's been a huge amount of attention and investment and, well, honestly, hype directed at these currencies. And I'm not going to comment or speculate on the current or future exchange rates, but I think we'd all agree that anyone looking to buy a cryptocurrency should really know what it is. And I don't just mean in terms of analogies with vague connections to gold mining. I mean an actual direct description of what the computers are doing when we send, receive, and create cryptocurrencies. One thing worth stressing, by the way, is that even though you and I are going to dig into the details here, and that takes meaningful time, you don't actually need to know those details if you just want to use the cryptocurrency. Just like you don't need to know the details of what happens under the hood when you swipe a credit card. Like any digital payment, there's lots of user-friendly applications that let you just send and receive the currencies without thinking about what's going on. The difference is that the backbone underlying this is not a bank that verifies transactions. Instead, it's a clever system of decentralized trustless verification based on some of the math born in cryptography. But to start, I want you to actually set aside the thought of cryptocurrencies and all that just for a few minutes. We're going to begin the story with something more down to earth: ledgers and digital signatures. If you and your friends exchange money pretty frequently, paying your share of the dinner bill and such, it can be inconvenient to exchange cash all the time. So you might keep a communal ledger that records all of the payments that you intend to make some point in the future. Alice pays Bob $20, Bob pays Charlie $40, things like that. This ledger is going to be something public and accessible to everyone, like a website where anyone can go and just add new lines. And let's say that at the end of every month, you all get together, look at the list of transactions, and settle up. If you spent more than you received, you put that money in the pot, and if you received more than you spent, you take that money out. So the protocol for being part of this very simple system might look like this. Anyone can add lines to the ledger, and at the end of every month, you all get together and settle up. Now, one problem with a public ledger like this is that anyone can add a line. So what's to prevent Bob from going and writing Alice pays Bob $100 without Alice approving? How are we supposed to trust that all of these transactions are what the sender meant them to be? Well, this is where the first bit of cryptography comes in: digital signatures. Like handwritten signatures, the idea here is that Alice should be able to add something next to that transaction that proves that she has seen it and that she's approved of it. And it should be infeasible for anyone else to forge that signature. At first, it might seem like a digital signature shouldn't even be possible. I mean, whatever data makes up that signature can just be read and copied by a computer, so how do you prevent forgeries? Well, the way this works is that everyone generates what's called a public key-private key pair, each of which looks like some string of bits. The private key is sometimes also called a secret key, so that we can abbreviate it as SK, while abbreviating the public key as PK. Now, as the name suggests, this secret key, it's something you want to keep to yourself. In the real world, your handwritten signature looks the same no matter what document you're signing. But a digital signature is actually much stronger, because it changes for different messages. It looks like some string of ones and zeros, commonly something like 256 bits, and altering the message even slightly completely changes what the signature on that message should look like. Speaking a little more formally, producing a signature involves a function that depends both on the message itself and on your private key. The private key ensures that only you can produce that signature, and the fact that it depends on the message means that no one can just copy one of your signatures and then forge it on another message. Hand in hand with this is a second function used to verify that a signature is valid. And this is where the public key comes into play. All it does is output true or false to indicate if this was a signature produced by the private key associated with the public key that you're using for verification. I won't go into the details of how exactly both these functions work, but the idea is that it should be completely infeasible to find a valid signature if you don't know the secret key. Specifically, there's no strategy better than just guessing and checking random signatures, which you can check using the public key that everyone knows. Now think about how many signatures there are with a length of 256 bits. That's 2 to the power of 256. This is a stupidly large number. To call it astronomically large would be giving way too much credit to astronomy. In fact, I made a supplemental video devoted just to illustrating what a huge number this is. Right here, let's just say that when you verified that a signature against a given message is valid, you can feel extremely confident that the only way someone could have produced it is if they knew the secret key associated with the public key you used for verification. Now, making sure that people sign transactions on the ledger is pretty good, but there's one slight loophole. If Alice signs a transaction like Alice pays Bob $100, even though Bob can't forge Alice's signature on a new message, he could just copy that same line as many times as he wants. I mean, that message-signature combination remains valid. To get around this, what we do is make it so that when you sign a transaction, the message has to also include some sort of unique ID associated with that transaction. That way, if Alice pays Bob $100 multiple times, each one of those lines on the ledger requires a completely new signature. Alright, great. Digital signatures remove a huge aspect of trust in this initial protocol. But even still, if you were to really do this, you would be relying on an honor system of sorts. Namely, you're trusting that everyone will actually follow through and settle up in cash at the end of each month. What if, for example, Charlie racks up thousands of dollars in debt and just refuses to show up? The only real reason to revert back to cash to settle up is if some people, I'm looking at you, Charlie, owe a lot of money. So maybe you have the clever idea that you never actually have to settle up in cash as long as you have some way to prevent people from spending too much more than they take in. Maybe what you do is start by having everyone pay $100 into the pot, and then have the first few lines of the ledger read, Alice gets $100, Bob gets $100, Charlie gets $100, etc. Now, just don't accept any transactions where someone is spending more than they already have on that ledger. For example, if the first two transactions are Charlie pays Alice $50 and Charlie pays Bob $50, if he were to try to add Charlie pays you $20, that would be invalid as if he had never signed it. Notice, this means that verifying a transaction requires knowing the full history of transactions up to that point. And this is, more or less, also going to be true in cryptocurrencies, though there is a little room for optimization. What's interesting here is that this step removes the connection between the ledger and actual physical US dollars. In theory, if everyone in the world was using this ledger, you could live your whole life just sending and receiving money on this ledger without ever having to convert to real US dollars. In fact, to emphasize this point, let's start referring to the quantities on the ledger as ledger dollars, or LD for short. You are, of course, free to exchange ledger dollars for real US dollars. For example, maybe Alice gives Bob a $10 bill in the real world. In exchange for him adding and signing the transaction, Bob pays Alice 10 ledger dollars to this communal ledger. But exchanges like that, they're not going to be guaranteed by the protocol. It's now more analogous to how you might exchange dollars for euros, or any other currency on the open market. It's just its own independent thing. This is the first important thing to understand about Bitcoin, or any other cryptocurrency. What it is a ledger. The history of transactions is the currency. Of course, with Bitcoin, money doesn't enter the ledger with people buying in using cash. I'll get to how new money enters the ledger in just a few minutes. But before that, there's actually an even more significant difference between our current system of ledger dollars and how cryptocurrencies work. So far, I've said that this ledger is in some public place, like a website where anyone can add new lines. But that would require trusting a central location, namely, who hosts the website? Who controls the rules of adding new lines? To remove that bit of trust, we'll have everybody keep their own copy of the ledger. Then when you want to make a transaction, like Alice pays Bob 100 ledger dollars, what you do is broadcast that out into the world for people to hear and to record on their own private ledgers. But unless you do something more, this system is absurdly bad. How could you get everyone to agree on what the right ledger is? When Bob receives a transaction, like Alice pays Bob 10 ledger dollars, how can he be sure that everyone else received and believes that same transaction? That he'll be able to later on go to Charlie and use those same 10 ledger dollars to make a transaction? Really, imagine yourself just listening to transactions being broadcast. How can you be sure that everyone else is recording the same transactions and in the same order? This is really the heart of the issue. This is an interesting puzzle. Can you come up with a protocol for how to accept or reject transactions, and in what order, so that you can feel confident that anyone else in the world who's following that same protocol has a personal ledger that looks the same as yours? This is the problem addressed in the original Bitcoin paper.